which one, or before anyone tell me, and I want you to focus on the formula where stress X is equal to mz or minus mz over izzzy. So can anyone tell me which cross section is under symmetrical loading or symmetrical bending? Cross section 1, cross section 2, cross section 3. And I want you to focus on the formula where stress X is equal to minus mz over izz multiplied by y. And I will further elaborate that over here, these are all your y distance relative from the centroid that is along the z-axis. Okay, which one is under symmetrical loading? Or yeah, which one? Anyone? Okay, let's start. Yeah, let's start with which one is under symmetrical loading. Cross section 1, cross section 2, or cross section 3? Anyone? Of them, okay? Because the verticalized split line applied that way. Lucia, you're right, is not, you are asking me of them. Yes, the answer is yes, it's of them. Okay, but that's not the reason. There's nothing to do with the vertical split line. Okay, so all of them, okay, all of them, okay, are under symmetrical bending. Okay, and I will tell you why. Okay, so if you look at the formula where stress X is equal to minus mz izzy. Okay, so if you look at all this, if you look at, okay, I will change this. I will call this y1, 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 and then on the opposite end is y2. Okay, and if we were to focus on 2 points, okay, let's focus on point alpha and point beta. Okay, point alpha. So if you look at point alpha and point beta, y is equal to y1 for both alpha and beta. So therefore, right, stress X alpha is equal to minus mz over izz multiplied by y1. And coincidentally, this is also equal to stress in the x direction for point beta. Because alpha and beta, they share the same y value. So therefore, okay, stress X alpha at point alpha is equal to normal stress at point beta. So when this condition is achieved, is what we call symmetrical bending. Okay. Then if we were to look at point I and J again, right? We know that y is now equal to what? y2, right? So if you look at I and J relative to the centroid that is on the z-axis, okay? So over here again, you have stress X point I is equal to minus mz over izz multiplied by y2, and this is also stress X about point J. Okay, so again, therefore, stress X at point I is equal to stress X at point J. Okay, so what did we conclude? Okay, we now know that whether it is symmetrical or unsymmetrical, right? We cannot tell, sorry, symmetrical or unsymmetrical or symmetrical bending, we can't tell by the loading condition. It's all based on what? Stress field. So whether, this is important, okay? So whether the structure is under symmetrical loading or bending, sorry, right? It is dependent on the stress field. Okay? Is dependent on the stress field distribution. More important than anything else, okay? Dependent on the stress field, okay? And what is so unique about symmetrical? So in symmetrical bending, the moment or there is only one moment acting on either the Z or Y axis. Okay. So let me elaborate on that. Okay. Now, if we now have a structure now, okay, I'll change to another page. Anyone, any questions so far? Anyone, please. Okay. Oh, sorry. I should turn this on. I don't want you all to feel like you're lonely. Okay. So now, uh, I'm going to. So the moment can only be acting on one axis only. Okay. It can be either on the Z or on the Y. Okay. So let me elaborate what do I mean by that. So now, if we have a structure in, I'm going to sketch this in 3D now. Okay. So if we have a structure, let me have so if this is our structure, so let's assume our structure is built in. Okay. You actually know. Let's assume our structure is built in. And then I will sketch our transformation. This is my X. This is our Y. Okay. And then over here, this is our Z. Okay. So now, if we have a moment acting on along the Z-axis, so what do I mean by that? So I'm going to copy and paste this twice. So later on, I don't need to draw again. Okay. Now, if we have an applied moment, so if we have an applied moment, okay, acting this way, so I use right hand rule. The formula that we will be using will be stress X is equal to minus mz over izz multiplied by y. Okay, so that is the moment applying on the z-axis, and this is what we call symmetrical bending. Or if we have another situation where the moment is applied, where the moment is applied along the y-axis. So this will be our moment about y. So you use right hand rule. That's how the moment vector look like. So over here, we are also calculating stress X is equal to minus my. Now this is over what? Iyy multiplied by z. Okay. So both of them is what we call symmetrical bending. As you can see, the moment is only applied on one axis. Okay, so that's how we classify symmetrical bending. Okay. In contrast now, I'm going to draw the example of unsymmetrical bending. Okay, so now let's look at how does unsymmetrical bending look like. Before I go on, anyone, any question, please? You can ask me or you can type. I can read. Anyone? Okay, I don't see anything, so I will proceed. So so we know, right? If it's symmetrical bending, the moment only can be applied on one axis. Okay, it's either my or mz. Now let's look at unsymmetrical bending now. Okay, let's look at a situation where we have unsymmetrical bending. So I'll write out the formula first. Yeah, I'll write out the formula first. Now is where we have stress X is equal to my over Iyy multiplied by z, and over here you have minus mz over izz multiplied by y. So in unsymmetrical bending, as you can see now, right? As you can see now, the moment is applied in both y and the z-axis. Okay, so for unsymmetrical bending, the moment is applied both in the y and z axis. Okay, so both. So now let me do a sketch. Now, how does this look like now? Okay, how does this look like? Okay, so I'm going to do a sketch now. Okay, again, I will draw a cantilever beam. Okay. Okay, so this is our cantilever beam now. I will sketch out our transformation.